and I want to clarify what I mean with seniors. Seniors means in this talk people over 65. So no matter how active you are, how young you feel, it's just the age group, general age group, and it's taken generally people over 60, 65. So first question is, who has had as a child the measles? I mean, pretty much everybody. I mean the disease, not the vaccine. We're a bit too old to have gotten the shot. More difficult question, who knows of somebody or somebody who was paralyzed by polio? Quite a few people. Also, we were too old to be vaccinated. We know people who were not vaccinated. The vaccine was introduced around the time when we were young. So as such, I would expect you to be a fairly easy public, because you still can remember the problems with infectious diseases and the time before vaccinations. And vaccinations, they are a bit the victims of their own success. People, youngsters nowadays, when I talk to students, they have forgotten about these diseases. They don't know what it is to get measles, to get tetanus, to get diphtheria, to get polio. They are vaccinated against all of that. The disease has disappeared from the consciousness of the public. So, first thing, what happened? Who am I? I'm a biologist by training, and I have worked for almost 40 years in the wider field of immunology. I was a professor at the Université de Sherbrooke for 20 years, where I taught immunology and genetics. I have never worked directly in the field of vaccines, but I have always been fascinated by vaccines and infectious diseases, and it has become a bit of a scientific hobby for me, and I have given a number of general audience talks on vaccines and pandemic threats over the years. I have to say, and I have to stress, that I'm not a medical doctor. I'm not qualified to give you medical advice. I can tell you what I do myself and what is my own opinion. I'm more, what is going on here? I'm more of a mad scientist type. I'm also doing a bit of woodworking. This was my first project enabled by the shed. So I like working with wood as well. The working title for me was Vaccines for Seniors, the Good, the Bad and the Ugly. And I think you're old enough to get my jokes. That was when I realized it was time for me to retire, when I realized that the students had no idea who I was talking about. Okay, the good. Vaccines are the only real and proven way to stimulate the immune system. So all these little products that say that they stimulate the immune system, most of them are just nothing. They don't do anything, or they do something quite weird. Vaccines have saved hundreds of millions of lives, billions of lives probably, also in seniors, and vaccines are extremely safe, as they should be, because we give them to a very large number of people, and people who are in good health at the time. But of course they are medicines like any other type of medicines, there are side effects, possible side effects, and there are possible risks involved, and we're going to talk about that a bit later. Okay, the bad is that in older people, just like anything else, stuff doesn't work as well as it used to work. There is no surprise here. The immune system in older people works less well than in younger people, and there is the terms of immunosenescence, immune aging, and there is also a chronic low-grade inflammation, which is termed inflammaging, that can have a negative effect on what's called the health span, how long you feel healthy and active. So they have important effects on our health, and therefore trying to rejuvenate, although there is no treatments at the moment which are in practice, but the idea of trying to keep our immune system younger might have a big effect on our general health. But there is also potentially, it is risky because it might cause autoimmunity. Autoimmunity is when our immune system attacks ourselves. And there is some evidence for that as well. We'll talk about this a little bit later. Okay, the ugly, yeah, here you got him.
Oh, God.
It's swapping. It's coming, the mixed messages that he gets. If you look now, a US poll says 3/4 of the American population either think that RFK Jr. does not recommend the measles, mumps, rubella vaccine, or they are not sure what he actually recommends, which is pretty much the message you get from him. So that's pretty bad. And some of it is going to come over the border as well. So that is something that motivates me to be here today and to talk to you to try to counteract that. We'll start with a short introduction to vaccines and to the immune system. I love this photo. Immunity originally is a term coined in ancient Greece and meant an exemption from paying taxes. You still have this sense in diplomatic immunity, parliamentary immunity, so this is the original term. The immunological immunity was also one of the first descriptions that we have is from ancient Greece, from Thucydides, who wrote about the Peloponnesian Wars, and he described the plague of Athens. It's still not clear what the disease was, but it was devastating Athens. And he described that people were very much afraid and didn't want to deal with the people who were dying in the streets. And the only people who dared go and try to help these people were those who had had the disease themselves and had survived, and therefore they knew that they would not get the disease themselves a second time. So this is what we all know about the immune system. If you've had measles once, you won't get it again. So it's this quite amazing capacity of the immune system to make an apprenticeship, to learn from an infection and to protect us against a reinfection, to develop a kind of memory against this disease. And this is quite unique in biology. The only other system is our memory in the brain, where we remember things, but that works, of course, completely differently. So now a little bit more details. Which are the cells that actually give us this memory? They're called the adaptive immune system because they do this learning process. So on the one hand, there are the B cells. B cells produce antibodies, these Y-shaped molecules which, like intelligent bombs, are secreted by the B cells, and they latch onto the pathogens and then lead to their destruction. A bit less well known are the T cells. T cells, we have two different main kinds. There are the killer cells. Killer cells, for example, because they kill cells which are our own cells, which are infected by viruses. Viruses have to get inside our cells in order to reproduce, and the cytotoxic cells are there to kill these kind of cells. There is also a type of cells which are called the helper cells. They are necessary for communication and regulation of the immune system. They are extremely important. The immune system is all about communication. It's all communication of different types of cells that talk to each other and control each other and stimulate each other, and the helper cells are extremely important in this. These three cell types are the ones which give us a long-term memory with long-lived cells that live for years. You know, as such, you expect to be still protected against measles. It has been shown that the protection lasts for your lifetime as such, if it works all well. So these are the long-lived cells that give us that. But the adaptive immune system is only one of the two main branches of the immune system. The adaptive immune system takes about a week to get into gear properly. So if you have a pathogen like a bacteria or a virus that divides every half an hour, of course you're dead, because before your adaptive immune system has come into gear. So there is a rapid deployment force, which is called the innate immune system, that has two main functions. One of the functions is to, of course, to slow down the expansion of the pathogens. It can't eliminate it completely, but it slows down the expansion, and the other main function is to stimulate the adaptive immune system and to stimulate the B cells and T cells, which are then going to provide the long-term memory and the long-term protection against the disease. So again, the communication between the different types of the immune system is extremely important. So as such, a vaccine is simply a deep fake of a pathogen. It looks like a pathogen, and it stimulates an immune response. Our immune system thinks it is confronted by a pathogen, but it is a fake pathogen in the sense that it doesn't make us ill, which is of course the whole point, because if we would get ill, there would be no use to this. So the criteria to get a good vaccine is it has to be safe. That's the first criterion. Of course, it mustn't make us ill. It has to be efficient and give us long-term protection, ideally for years. And most vaccines still nowadays aim to give us the production of protective antibodies. We're going to talk about that a bit later on again. Thus, the vaccines, as such, biologically speaking, they don't really do anything miraculously. They exploit our natural capacity of the immune system to mount a long-term memory response. It's what the immune system does normally to protect us from reinfection. The immune system, it is confronted with a reinfection, but we have contourné, we have circumvented the primary infection with the pathogen by starting on step 2 before we have actually got to step 1. This protection is specific in the sense that a measles vaccine won't protect you against mumps, okay? You can't just stimulate the immune system. That doesn't work. You have to do it specifically with the vaccine, and you have to have specific vaccines for specific diseases. We'll talk about a general stimulation of the immune system at the end of the talk, but that is something which does now recently has been shown to work, but it is risky in the sense of risking autoimmune diseases. Now, a short history of vaccines. There, smallpox is of course very important. Smallpox has devastated empires with a mortality of 20 to 40%. You got these pustules on the skin. There has been a practice to try to protect from smallpox, variola, since at least the 12th century in China. It was also used in Africa and in the Middle East, probably brought over from via the Silk Road in the Middle East. What was done was to wait for these pustules to fall off, to let them dry, grind them into a fine powder, and then inject them or insufflate them into the nasal cavities via these long tubes. I have no idea why the tube here needs to be that long, but this is the historical picture. This works. Okay, this works. This was, if you want, it was the first vaccination. It was brought to Great Britain in the 18th century. About 1720, became quite popular, but you can easily see that this is also a risky procedure. If the virus has not been completely inactivated, you might actually transfer the disease, and there is a risk of infection with a disease of several percent. And for example, King George III of England lost one of his sons to this practice of variolation, which leads us to Edward Jenner, a country medical doctor in England. Edward Jenner had realized that the young women who were milking the cows, the cowgirls, here you got one of them, that they got infected quite frequently by the cow version of the pox, which Jenner named Vaccinia, from Vacca the cow, and these girls were protected from smallpox. So he had the idea well, if I voluntarily infect somebody with the cowpox version, this person might be protected from smallpox. So in 1976, Jenner performed a clinical trial. He took the 8-year-old son of his gardener, James Phipps, and transferred some of the pus off the hand of one of these cowgirls into James Phipps with a little cut on the arm. And James Phipps got ill. He got a bit of a fever, but he recovered quite rapidly. And a few weeks later, Jenner performed the variolation on the little James Phipps. I mean, of course, nowadays he would be in prison because this would never get through the ethics committee. But you have to see that this, at the time, was at a time when half of the children in the family died before the age of 5 years. So it was completely different times. Jenner repeated these procedures on several other people, including his own son, and then published his findings, and it was quite quickly accepted. And this is why we're talking nowadays of vaccines and vaccinations, because of this procedure. It comes from the vacca, the cow, the vaccinia, and we're talking about the vaccinia virus, which is originally the cow version of the smallpox, okay? This is how we got to vaccines. This picture I show you because of the booster shots, repetitions with the same vaccine, which are re-challenges with the same pathogen or the same antigen to increase the effectiveness of our immune system. Our immune system, when it is put in contact with the vaccine, improves the immune response in terms of quantity. There are more cells specific for the pathogen, and the B cells produce better antibodies. The quality of the antibodies actually increases, and it increases the duration of the protection. So, herd immunity. Why is vaccinating not just an individual decision? This is due to the fact that if enough of the population is vaccinated, the pathogen can't circulate anymore. So if you are vaccinated and you're protected from the disease, not only do you not get the disease, you also don't give it to somebody else. So this is what herd immunity is all about. And little Dennis here, he has got the idea sort of half right. It is true that if everybody else is vaccinated, you don't as such need to be vaccinated, but it's only half true, because if everybody has got the idea, it doesn't work. So this is why you have to be vaccinated. The risks. Vaccines are amongst the most closely, or they are the most closely supervised medicines we have got. But of course, as I said, they are medicines like any other medicine, and the notion of zero risk just is not possible. So there are side effects and there are risks involved. The most famous instance here is the so-called Cutter incident, but that is not an inherent risk of vaccines. This was a straightforward accident in the Cutter facility where a batch of poliovirus, the Salk vaccine, was not properly inactivated, and children were injected with live poliovirus and got paralyzed. However, a real inherent risk of polio is, for example, with the oral polio vaccine, which is still used in developing countries nowadays. In about 1 in 500,000 cases, the virus reverts to its virulent form and can give the disease to the children. And nowadays that polio is so low, the large majority of polio which we see is actually due to this vaccine polio. There is now a new strain which has a much lower risk than this number 2 strain here. So a good illustration of the risk is, for example, in the measles vaccine. The measles vaccine is known to cause acute encephalitis, inflammation of the brain, in about 1 in a million cases. However, the actual measles virus has a rate of about 1 in 1,000 for acute inflammation. So it's 1,000-fold more frequent, and it appears that is a complete no-brainer that it is a good idea to vaccinate. But however, if there is no measles about, these cases have disappeared, and the parents of the child who got the 1 in a million bad luck, they will feel bad about having vaccinated their child because they've never seen the other children who would have been damaged by the encephalitis. Another well-known case is the Guillain-Barré syndrome with the flu vaccination. Guillain-Barré is an inflammation of the peripheral nerve, probably an autoimmune disease, quite rare, and you can get it normally after infection with viruses, respiratory viruses or gastrointestinal viruses. And there is a certain risk that you could get it from the vaccination, but it is in the same order or lower than you actually get it from the actual disease. So what's in a vaccine? There is the active ingredient, which we call the antigen, which are either, there are 2 major types. There are either the live attenuated vaccines, so it's a weakened form of the pathogen, which has been weakened so that it doesn't give you disease. This is, for example, the MMR vaccine, measles, mumps, rubella, or all the others which we're lumping together here to the non-live vaccines. And then, depending on what the type of vaccine is, you can have for the non-live vaccines, chemicals which inactivate the virus. You can have adjuvants, we're going to look at that, and eventually preservatives here, the thimerosal, which has made some noise, is an example. The aging immune system, there is the buzzwords immunosenescence, immune aging, and inflammaging. We're going to look at that in a bit more detail, but as we've said, with Bill, aging is not all bad. There's also good things from aging. This is, for example, my first retirement project. I'm quite proud of it. Okay, immunosenescence. It's simply, well, it's not simple. It's not simple. All the parts of our immune system age, and there is no easy fix to make it better. However, in people that live for a very long time into their 90s in very good health, if you look at their immune system, they show the markers of a much younger immune system. So it has a large impact on our health. And there are some news. There was a paper last year that made a lot of noise, where a relatively simple treatment of depleting some stem cells in mice had a big effect on the performance of these mice in their immune system. Unfortunately, it's in mice. We are not mice, but it is a treatment that might be transferable relatively easily to humans. The inflammation, you all have a general idea what inflammation means: redness, swelling, hurt, what you get after a vaccine shot. Inflammaging is the chronic low-grade inflammation that may have a large impact on diseases like cancer, heart disease, Alzheimer's. So it's an important component of disability and mortality. There are some specific changes in the immune system. One of them is that the T cells are called T cells because they are produced in the thymus, a small organ sitting on top of our heart. The thymus starts to lose its function very early in life, right after puberty. It's linked to the sex hormones, and it's pretty much finished at the age of 50. So everybody in here, you got no functional thymus anymore. Which means from the age of about 50, we have to live with long-lived cells. Why this is so is not clear. It may protect us from autoimmune diseases, it may be good for something, but we don't really know. Clearly, older people can mount immune responses to new pathogens and new vaccines, as we have all seen with the COVID vaccine. It worked relatively well also in older adults. So we can mount immune responses to new vaccines, but it works less well. There is a decline for B cells as well, but it's less clear and it comes later in life. Now, strategies to boost vaccine efficacy in older people. There is the simple way of increasing the vaccine dose. There are flu vaccines which do that. There are adjuvants, products that help the immune system. We're going to talk about that, and the delivery, where you inject the vaccine, and it is clear that the normal standard intramuscular injection is not necessarily the best way to give a vaccine. The muscle is not an immunological, very active tissue. So there is new development to give the vaccine via skin patches with these microneedles that dissolve and disappear. They are biodegradable. Our skin is an immunologically very active organ, and there are lots of immune cells sitting in there. Other effects are studied at the moment. There's things like exercise, calorie restriction, intermittent fasting. Intermittent fasting would, for example, mean you take in your calories during an 8-hour period, and then you have 16 hours where you drink only water. These procedures, calorie restriction and exercise, prolong life in mice. But we're not mice, I say it again. A lot of stuff works in mice. They clearly prolong life. Calorie restriction, not eating too much, controlling the weight without being malnourished, has clearly an effect of the lifespan of mice. There are certain drugs like metformin and rapamycin. Metformin is a type 2 diabetes drug, a standard type 2 diabetes drug. Rapamycin is an immune suppressant at higher dose. It's used in organ recipients, organ transplant recipients. Both drugs prolong the life of mice. Not necessarily linked to the immune system, but they have an effect. There are supplements like zinc, for example. Most older people apparently have a zinc deficiency, so that has some effect in experimental animals. All this is being studied at the moment, but nothing of this is currently in clinical practice. But there might be coming something in the future. Now let's look at the adjuvants. Adjuvants comes from the Latin adjuvare, help or contribute. It has two major effects. One is to prolong the availability of the antigen, and the second one is to provoke the innate immune system, the rapid deployment force, to stimulate the adaptive immune system better. So in an approximation, it provides some inflammatory stimulus to the immune system. There are relatively few adjuvants for human use. They're all relatively weak. The longest known one are aluminium salts, which have been used since 1925. They work really well, but they are a relatively weak stimulus. There's never been any problems with these. A lot of the standard pediatric vaccines use these aluminium salts. Newer adjuvants are oil and water emulsions like the MF95 from Novartis, which is used in flu vaccines, or the AS03 from GlaxoSmithKline. If you have been vaccinated in 2009 against the swine flu, you received the AS03, which was used the first time at that point. If you have a question, what is an oil and water emulsion? Mayonnaise is an oil and water emulsion, with the lecithin from the egg yolk being the emulsifier. One interesting story I came about when I was reading up for this lecture was the connection of the vaccine, giving the vaccine at a certain time of day. And I came across this study that looked at other studies. They found 17 studies which had looked at the time of day of the vaccination and compared the immune response. and 11 of these 17 studies showed an effect depending on the time of day, and 10 out of these 17 studies where it works better if you get your shot in the morning. The other 6 that did not show any effect were largely in younger people, so older people over the age of 65 clearly showed an effect, and it worked better if you get your vaccine in the morning. So, vaccines for seniors. There is a number of them. Tetanus, diphtheria, seasonal flu, COVID-19, pneumococcus, shingles, and the new kid on the block, RSV vaccine, the respiratory syncytial virus. Now, when I study this, I sometimes come across conflicting information, and I really don't like that. For example, if you look at Health Canada, it says for the diphtheria tetanus toxin, a booster dose every 10 years for adults. If you look, and this is the official Health Canada website, if you look at the corresponding site of Quebec, you get 1 dose at 50 years of age. So, what the hell? It must be that the Quebecans have a better memory. I mean, they got it on their number plates, so very confusing. And if you look here, the flu vaccine, it says here every year from the age of 75. They give it out from 6 months onwards for free, but they recommend it only for people over 75. This is not X, Twitter, or Facebook. These are official government websites. They can't get their act together. There's not even COVID on this sheet of the government. So this doesn't make it easier when you try to research this kind of stuff. So let's look at the different vaccines. Influenza. Influenza is an RNA virus. You have maybe heard of these nomenclature here, H1N1, H5N1 for the avian flu. These are the nomenclatures of the different types of viruses. The H is for the hemagglutinin and the N is for the neuraminidase. The hemagglutinin is for getting into the cell. The neuraminidase is to get out again. The viruses, as I said, are obligatory intracellular parasites. They need to get into our cells via a receptor that's hijacking a molecule which is expressed on the surface of our cells, which normally serves quite a different purpose, which is hijacked by the virus to get into the cells. In this case, this is the molecule in case of the influenza, it's the HA molecule, and the receptor is a complex sugar on the surface of our cells. Now, vaccines generally are made to produce a lot of antibodies and specific antibodies. And for example, in case of COVID, the gold standard of traditional vaccinology is to produce what is called neutralizing antibodies. Antibodies which prevent the interaction of the molecule that helps the virus, in case of COVID, the so-called spike protein, into the interaction with its receptor and to get into the cell. This is what traditionally is aimed for, and for example, in case of COVID, all the different vaccines are using the spike protein as an antigen. So why do we have so much trouble with the flu? As such, we make a good immune response against flu, but the problem is that flu is a master of disguise. It's hiding from our immune system. I have to say here, all pathogens have systems and strategies to circumvent our immune response. Otherwise, they would just not be pathogens, and our immune system will dispatch them very, very rapidly. So all of them have strategies. In case of the influenza, is that the replication machinery of the genome of the influenza is quite sloppy and makes a lot of mistakes, which means there are lots of variants generated which present the HA molecule and also the other molecules in different colors, different flavors, different shapes, and that means you have to periodically adjust the composition of the vaccine. It's a bit of a misconception that's circulating that the vaccine composition is changed every year. There's a WHO committee that decides twice a year, about 6 months before the flu season, which strain to use for the next flu vaccination season. So southern and northern hemisphere separately, about 6 months beforehand, and this makes it that we have to do an annual vaccination. That is also necessary because the immunity wanes relatively rapidly. And there are, just as an information, normally for the flu vaccine, there are normally 3 or 4 different strains in the flu vaccine of the different flu types. This year it's a trivalent flu vaccine. The second strategy is much more drastic and much rarer. That is, if 2 different strains of viruses happen to infect the same cell, the genome segment, there are 8 of them, they can mix up and a new virus can be produced. This is why it is impossible at the moment to produce a vaccine against the avian flu, which might become pandemic at some point, because we don't know what it's going to look like. So this is major flu pandemics have been associated with this second evasion strategy, which is called the antigenic shift. Most flu vaccines are produced in hen eggs, and they produce the influenza HA molecule. The neuraminidase co-purifies with it. So most of them are produced in hen eggs. There are some other methods. There is one vaccine which is a live attenuated vaccine, but it is only given for people up to 59 years old in Canada. That probably doesn't mean that it doesn't work well for older people, it just has not been tested so far. Okay, there are currently in Canada 7 or 8 licensed vaccines. There is a high dose with 4 times more HA than the standard. There is the intranasal, which is from 2 to 59 years, homologué, I don't know, licensed. And there is one with an adjuvant, the MF95, but in Quebec you can only get one of 2 types, which is the flu viral, which is pretty much the only one for the older population, and the flu mist for the younger population. So it's pretty much the only one you can get. The efficiency is around 50% of the vaccine, so you got about 1 in 2 chance that the vaccine will actually protect you. That is not particularly brilliant, but it's also better than a kick in the pants, okay? And it's a lot better than playing 649. And you have to see, if you get the vaccine and you don't get the disease, you don't give it to somebody else. And if somebody else gets the vaccine and is protected, it doesn't give the disease to you. COVID-19, you all heard about COVID-19. It was a big deal. In 2021 in Canada, it was the 4th most frequent cause of death. This was with the vaccine available already largely throughout the year. So it was really a big deal, and it was also the advent of mRNA vaccines. What we all got were mRNA vaccines. What are mRNA vaccines? The genetic code is normally stored in DNA. You all know this business of the double helix. And to make proteins in the end, you need an intermediary, which is called the messenger RNA, which is a copy of the sequence of the DNA on a single-stranded molecule, which then gets translated into protein. And the protein is actually then the molecule which does the job in our cells and which is the target for the vaccines. There are the 2 companies which got very rich on this, Pfizer, BioNTech, and Moderna, to make these vaccines. These were the first mRNA therapeutics that were used in the world for anything. And in 2023, Kathleen Carrico and Drew Weissman got the Nobel Prize for this. And this year, RFK Jr. decided to stop all research and development in mRNA vaccines and mRNA medications. Originally, we made quite a good immune response against COVID, but the immunity wanes quite rapidly. It loses its strength. It's not quite clear why that is so. And of course, you all know the rapid evolution of new strains. This is only to the end of 2022. You all remember the Omicrons. There were several Omicron strains which developed, and this of course continued like that. I don't know, I got vaccinated on Saturday. I don't know whether it's my 5th or my 6th boost that I got, because it evolves and it continues to evolve. We got again about 50 to 60% efficacy for the COVID-19 vaccine against hospitalization. So not super good, but also not super bad. Shingles. Shingles is a reactivation of the chickenpox virus. So everybody who's had the chickenpox contains the virus, is not eliminated completely from our system, and it can reactivate. It is estimated that 1 in 3 older people gets shingles. It's a very painful disease. There is the nerve pain, the neuralgia. It can affect the face. It's the first cause of blindness in adults if it affects the optic nerve. There is a shingle vaccine called Shingrix from GlaxoSmithKline, which has been around for a few years now, not too long. It's supposed to be quite effective and long-lasting. It works well also in older people. It's apparently 90% effective, and people, there used to be another vaccine which was a live attenuated vaccine called Zostavax. It's recommended to get the Shingrix if you had the Zostavax beforehand. Pneumococcal, Streptococcus pneumoniae. It's a bacterium found in the respiratory tract. Many people are carried around without it making a problem. It's free, the vaccination, for people over 65 years. There are serious consequences if you get the disease, and 3,000 to 6,000 hospitalizations in Quebec a year. Let's skip this. Respiratory syncytial virus. That's the new kid on the block. It's problematic for infants and for older people. There is a new vaccine around. People over 65 years of age are at higher risk. The efficiency is high, 79, 80 to 90%. The vaccine is not free for people who are over 65 years old. You have to be over 75 and live either in a résidence pour aînés or have certain chronic diseases. So it's not free at the moment, and I think it's quite expensive. It costs about $200, if I got that right. However, there was a recent Canadian study done in Ontario where they found that people 65 and older were hospitalized for respiratory syncytial virus. They had a risk of poor outcomes which was higher than influenza infection, urinary tract infection, or fractures. So they recommend that people over 65 who are also in good health might benefit from getting this vaccine. I have decided on the strength of this that I'm going to get it. I just want to mention that the FDA now requires a warning on the vaccines for Guillain-Barré syndrome, but the incidence of the Guillain-Barré in this case is about a bit less than 1 in 100,000, which is very much in the order of the background occurrence in the general population. So you increase your risk maybe by a factor of 2, maybe less. So I think it's a risk you can live with. So I'm almost at the end. The outlooks. The outlooks would be universal vaccines. Wouldn't it be great to be vaccinated once against flu and be done with it? That is a problem. This is the structure of the AHA molecule. This is the pandemic virus of 2009. You can see the red balls are the mutations. You can see the mutation rate is much higher in this part, which is called the head, than in the stalk part. So if we could direct the immune response to the stalk part, we might get a much broader protective vaccine. There are some works in the works at the moment to try to do this. You cannot just simply chop off the head because the bottom will fall apart. So that doesn't work. You have to use other strategies. Immunotherapy of cancers. One thing I haven't talked about is our immune system plays a very important role in fighting off cancer. It's not clear how much, because it gets rid of probably of a lot of cancerous cells in the early stages. There has been in the last few years a new strategy which is called immune checkpoint blockade. There is a whole of negative regulation in the immune system to prevent the immune system of doing something bad to ourselves in the terms of autoimmune diseases. And you can now, with this immune checkpoint blockade, take off the brakes of the immune system to make it work harder. And this is the new strategy which got a Nobel Prize in 2018 for Allison and Honjo. This has been used here for either non-small lung cancer cells or melanoma. The curves are survival curves. So every time, this is time, 40 months, 3.5 years. You start at 100%. Every time the curve falls down a bit, somebody dies. The red is the immune checkpoint blockade, and very interestingly, the blue curve is patients who got the immune checkpoint blockade plus a normal standard COVID mRNA vaccine. So this is not a cancer vaccine as such. This is the normal, ordinary mRNA vaccine against COVID, and you see the survival rate almost doubles. This is huge. This is a huge effect, and there is certainly a lot to be done with that. Finally, in the end, vaccines against aging. There are a number of trials that try to prevent aging-related diseases with vaccines, like Alzheimer's, type 2 diabetes, hypertension, atherosclerosis, and so on. None of this is ready for rollout, but there's a lot of work going on for that. So there's stuff coming in that respect. The immune system can be useful for this as well. Okay, I'm finished now. Thank you.
Very good. Thank you very much, Victor. That was a great presentation, good education, and we all know we got to get our vaccine, right? That's right.
Well, I do it.